This video is about topic 3.8, which is representation of solutions. And the objective for this topic is to use particulate models for mixtures to represent the interactions between the components and to represent the concentration of the components. So we have to think about what's going on in the solution process. So this isn't just a static thing, it is a process that happens when you dissolve something. So when we talk about a solution of two liquids, words that you'll see are words like miscible and immiscible. So a miscible liquid is something that's soluble in any proportion. So if you have two liquids and we say that they are fully miscible, it doesn't matter what their proportion is, they are going to mix. If they're immiscible, they are not fully soluble in all proportions. So that's where you have two liquids that when you try to mix them, they're not going to be fully soluble. So a common immiscible liquid would be oil and water. That's one of the first ones that always comes to mind. When you mix them together, they're not going to be soluble. The other more common type of solution are solids in liquids. So when we think about how our different types of solids dissolve, we have to think about ionic versus covalent. So an ionic solid is, we can think of it in terms of extreme polarity, because remember, polarity is a scale with ionic being on one end and nonpolar covalent being on the other. So in an ionic solid, if we think of it as extremely polar, it's going to break apart into its two ions, or more depending on the ratio, but it's going to break apart into its positives and negatives. Let's say it that way. When they do that, the positives and negatives are going to interact. They're going to form an ion dipole interaction with the water in the solution. So we're assuming here that we're dissolving a solid in water. So the ionic solids have broken apart into their positives and negatives. The positives and negatives are going to be attracted to the positive and negative side of water. So they're going to form that ion dipole intermolecular attraction. The same thing is going to happen with a polar solid. So a polar solid will dissolve in water because it's also polar, like dissolves like. And so if we have a polar solid, the same thing. The polar side of that polar covalent molecule will be attracted to the other part of water. The slightly positive is going to be attracted to the slightly negative. The slightly negative is going to be attracted to the slightly positive. So that will form either a hydrogen bond with water, or it'll form a dipole-dipole interaction with water. Nonpolar solids are typically not going to dissolve in water because they're not going, or at least they're not going to significantly dissolve in water because they have a very, very weak attraction to the water molecules. You might get a very small temporary induced dipole with water, but it's not very strong, and so they're not going to dissolve in water. So again, we think like dissolves like, and if we think of, so that means water is polar, so polar covalent are also going to dissolve in water, and then we can put ionic into that category if we think of ionic compounds as being extremely polar. So let's look at how we would draw this as a particle diagram. So it's pretty simple. You have so this is sodium chloride. So we have a sodium ion and we have a chloride ion. So sodium's positive, which means it's going to be attracted to the negative side of water. And the chloride ions are going to be are negatively charged. They're going to be attracted to the positive side of water. So if we look at our water molecules, our oxygen, which is what's in the middle, is going to have our partial negative, and our hydrogens are going to have our partial positives. So if you look at our green chloride ions, the water molecules surrounding them are pointing with the hydrogen or the positive parts in, and our sodium ion, which is positively charged, is surrounded by water molecules with the negative part or the oxygen part in. So we can draw it and represent it with those attractive forces in place. You can also look at this in terms of ratios if you're thinking about concentration. So you can use your particle diagram to represent concentration by thinking about the ratio of water, which is your solvent, to your solute, which is whatever it is that you're dissolving. So you can show that ratio, which will show your concentration. So that's how we can think about our solvation process and represent our solutions in a particle diagram format.